Alkene complexes. Right, so alkene complexes. I've talked briefly already about alkene complexes in this and they're obviously very important. Why are alkene complexes so important? Well, of course, the reason is when you're doing catalysis, it's very frequently an alkene complex that you want to do the catalysis to. It's often an alkene complex that you want to functionalize, or perhaps you want to polymerize it. So alkene complexes and their binding to transition metals plays an important role in subsequent reactivity of these. And actually, one of the very, very first organometallic complexes ever made, possibly the first that was deliberately synthesized or synthesized by man, was Zeis's complex. Now, Zeiss was one of those chemists that you could have back in the 19th century, early 19th century, who was a dab hand at all sorts of things. Nowadays, we all specialise, but Zeiss used to do all sorts of experiments in all sorts of areas of chemistry. And one of the things that he was doing is taking ethanol. He was taking ethanol and refluxing this platinum tetrachloride salt. So this is platinum in oxidation state 2, so the dipotassium salt of platinum tetrachloride in ethanol and refluxing it. And when he did that, he got out some beautiful crystals. So you can make an alkene complex by taking ethanol and refluxing it in the, with an oxidizing metal salt there. So this is an example of ethanol actually being reduced in the coordination sphere of the metal by refluxing it up. Okay, how do we make these complexes? Well, anybody remember this reaction? So you can irradiate your iron pentacarbonyl, knock off one of the carbonyl ligands, and coordinate the present cyclooctadiene molecule. You can do something similar with a diene. So this is butadiene. Butadiene is, well, a soluble gas. Okay, so this is when you take butadiene and your iron pentacarbonyl and you heat it up, you kick out 2 of the CO ligands and you substitute a diene. Now, do you think we could do that indefinitely to replace all of the CO ligands with diene molecules in that fashion? No, you can't substitute all of the molecules in this fashion because the back bonding increases to the remaining carbonyl ligands and they bond that much stronger and they're that much more resistant to being substituted. If you want to go straight to a diene complex, essentially what you need to do, let's go to this one here, what you need to do if you go straight to a diene complex is that you have to essentially work in the absence of if you want a complex that is like this, you have to work in the absence of carbon monoxide ligands. So if we take iron in the vapor phase and then you can co-condense them with a ligand, you can get some spectacularly exotic organometallic structures. An alkene ligand is a 2-electron donor. There are 2 electrons in a double bond. Those 2 electrons, let me rephrase that. There were 2 electrons in the pi cloud of a double bond, and it is that orbital that is being donated. Now, what about this structure here? This is a beautiful example. I hope some more of you dig out your numbers because this one here is a beautiful example of an electron counting problem. So here we have a rhodium complex. What is the electron count of one of the rhodium environments in this rhodium complex? So I'm talking about the electron count with respect to one of these rhodiums. Let's just think about what geometry this rhodium complex is. What is the geometry around rhodium in this complex? It's square planar, okay? So this is a square planar complex. Remember what rule we're expecting to apply for a square planar complex. Rhodium is in group 9 of the periodic table. A chloride ligand, an ordinarily bonded, sigma bonded chloride ligand, is a how many electron donor? 1. So 9 plus 1 is 10. Now this is the dative donation of a lone pair on the chloride ligand. So how much is dative lone pair donation? It's a 2-electron process getting up to 12, and an alkene ligand is a 2-electron donor, and there are 2 of them. So 12 plus 4 is 16. So this is a 16-electron complex, and you'd expect that. You'd expect a 16 electron complex because it is a square planar rhodium 1 complex.